Welcome to the October 2021 General Meeting of the Chicago Astronomical Society. Our speaker tonight is Jose Francisco Salgado. Jose is an accomplished photographer, best known to us for his photography of the Aurora Borealis. Jose is kind enough to share with us his techniques and equipment for photographing the aurora, as well as the scientific information that his photographs reveal. Jose holds a bachelor's degree in physics from the University of Puerto Rico and a PhD in astronomy from the University of Michigan. He is currently the executive director and co-founder of KV265, a nonprofit science and arts educational organization. Dr. Salgado collaborates with orchestras, composers, and musicians to present films that stimulate curiosity and wonder about the Earth and the universe. Jose, if you're ready, the meeting is all yours.
Thank you very much. Okay, so you know what? Let me get my earbuds so we don't get feedback. Okay, can you hear me?
I can hear you fine.
Wait. Regardless of what you choose, Zoom, has its own control. So you have to do it over there. So let's see, audio, speakers.
Okay, let's try now.
Well, I can hear you fine. Can you hear me?
Okay, good. Yeah, so regardless of what you choose on the computer, you have to do it on Zoom. Okay, well, thank you very much for the invitation. Delighted to chat with you about my work regarding the Northern Lights. So let me share the presentation with sound. Okay, can you see it?
Yep.
Okay, very well. Okay, well, let me tell you a little bit about the motivation or the origin of me photographing the Northern Lights. Some of you might know that I make these, we call them science and symphony films that get presented with symphony orchestras. And the idea is to bring science into non-traditional venues when it comes to science education. And an example of that is the concert hall, because people come to the concert hall to listen to music, not necessarily to be exposed to scientific visuals. And the concerts are preceded oftentimes by a lecture, or at the very least by an introduction where I put in context the visuals that people are going to see. So in 2014, we premiered this work called The Legend of the Northern Lights at Millennium Park. And for that work, I visited Yellowknife in the Northwest Territories of Canada to get the visuals. And that led to a second work and a third work about the Northern Lights. In total, we have like 11 films, and 3 of those are about the Northern Lights. So here's an example of one of these concerts in Singapore just before the pandemic. So now we have presented 10 films, working on number 11, and we have had like 238 concerts in in 15 years. So the works have reached 465,000 people there, right? Not online, not, we're not talking about likes and shares. We're talking about actually people coming to the hall or coming to a lecture and learning about the visuals, firsthand. So as I mentioned, Legend of the Northern Lights led to a second work by a Canadian composer, John Estacio. First one was composed by Chris Theophanidis specifically for the work. So we commissioned and collaborated with him. The second one, the music had already been composed, and I combined it with visuals that I had shot. And then the third one was also a commission from Boston Pops. And again, for that one, I didn't have to go back to Yellowknife. I just went into my archives. By then, I had visited Yellowknife every single year. So I have been amassing visuals of the Northern Lights. So what you'll see on this presentation, unless I, state it explicitly, everything has been shot by myself. So I started working with the Anchorage Symphony in Alaska, and by then I had this idea already. I mean, we were developing this idea of making a science and symphony film about the Northern Lights. So I started visiting, Anchorage for concerts to collaborate with orchestras, and of course at night I would go out and try to photograph the lights. The term Aurora Borealis was actually coined by Galileo in 1619, based on the Roman goddess of the dawn, and the Greek name for the north wind. Is, of course, from the northern hemisphere, you see the lights when you look in the northern direction, and they may look like a false, dawn, kind of like the zodiacal light. The zodiacal light is white, very, very white. And of course, with Northern Lights, you can see colors depending on the brightness, but at the very least, you should see some muted greens. I have also photographed them from Fairbanks. That's more England, right? Anchorage is by the water. Every time you're by the water, weather is going to be challenging because you might get a lot of cloud formation. If you go England, then the weather is more continental. And at the University of Alaska in Fairbanks, they actually have a research center and a site from where they launch rockets into the upper layers of the atmosphere to study the Northern Lights. I have also seen them from Iceland. Iceland, same situation with the weather, because it's an island. You're always close to the coastline. Weather is challenging. I'm not saying that it can be challenging. It is challenging. So been to Iceland twice, and the number of cloudy days per visit has been really, really high, and in two different seasons. I've been in April and in July, so it could be a challenge. But when you see them, hey, they're beautiful, and of course the landscape in Iceland is beautiful. You can also see them from flights. When you travel near northern latitudes, be it because you're going to Europe or returning from Europe, or in this case, returning from Alaska to O'Hare. So I saw them from northern Alberta. I've seen them from northern I should say from in Canada, from Alberta, like probably north of Calgary. So this is from one of those flights. I've seen them a couple of times. Now this one, it's one of those, if not the only photograph that it's not a mine. I've been to the South Pole. I've been to the South Pole Station, but during the spring, when we have 24 hours of daytime. But for those who go at night, and of course, if you go at night to the South Pole, you have to commit to like at least 8 months of your life, because Yeah, because they don't travel during the winter. Okay, they travel a few, you know, let's see, I think the earliest they go maybe in October, and then by February they're not going. They stop the flights. So yeah, so the people that they say winter over, it's 6 months of nighttime, and then of course pad that with a couple of months. So it's at least eight months that you're gonna be stranded there. But I've seen beautiful images like this one of the South Pole and the Northern Lights. And then, of course, you can see them from the International Space Station as well. The International Space Station has the orbit of it's inclined by almost 52 degrees, so it takes the ISS at least up to that, up to that latitude, and that's a great vantage point, because you're at the same height as the Northern Lights themselves. So I have an astronaut friend, Joseph Acaba, who has photographed them. So we have chatted about, the experience of seeing them from the ISS. The funny thing is that he has seen them from the ISS, but not from the ground. And then, of course, I've seen them from the ground, but not from the ISS. So would love to at some point offer a lecture with him, and we could talk about both perspectives.
Hello, Jose Francisco. This is Joseph Acala calling you from the International Space Station. I just wanted to say hello and wish you a very happy and safe New Year. I hope you are doing well. Take care. Bye-bye.
So that was a couple of years ago. He called me from the ISS, and I missed a call, but then I was so glad that I missed a call, because then he left me a voicemail message. So I told him, hey, you're part of my lecture now. Thank you so much for your kindness in thinking about me and giving me a call. I don't know exactly how it works. Probably they have an allocated amount of time, and they have a list, and they call people, and probably they say hi very quickly, and then on to the next one, So that was very kind of him. We gave a lecture together at Texas Tech in 2014. That's where we met. So we can see the Northern Lights on other planets as well. You need two key ingredients. The planet must have an atmosphere, because of course that is what's going to glow. That's the component that it's going to glow. And you need a magnetic field, because the magnetic field is going to guide and accelerate those high energy particles, mostly coming from the sun, through the atmosphere. Okay, so now that's very, very important, because, and of course, I know that you obviously you're into astronomy, and you like to get, you want to understand exactly how things happen, and avoid misconceptions, right? So a misconception is that people say like, oh, it's particles that come from the sun, and they buffet the Earth's atmosphere. Well, yes and no. Most of them come from the sun, but they to be trapped inside the magnetic field of the Earth itself, at the tail of the magnetic field. And then it is the magnetic field itself what's going to accelerate those particles towards the atmosphere and produce the Northern Lights that we see. Why is that important? Because, for example, Venus doesn't have a strong magnetic field like the Earth does, so it gets buffeted by particles continuously. But what it gets some kind of daytime aurora that it's not really very bright. Why? Because those particles coming from the sun at that speed do not have enough energy to produce the Northern Lights we see. Okay, so the particles come from the Earth itself, just before the northern lights are produced. Okay, so here you have some gas giants and Io displaying, different northern lights. Okay, and then I've seen them from Yellowknife, and I think from now on, yes, from now on, all of the images that I'll show are from Yellowknife. And because I take people to see the northern lights in Yellowknife, we can talk later on about Yellowknife. But look at these two fisheye images. It goes to show you that from Yellowknife, you can be absolutely surrounded, engulfed by the northern lights. Look at that second photograph where they're coming from all directions. Okay, they're coming from above, but 360 degrees around you. Okay, and I'll explain that why in a minute. I'll also show you a time-lapse sequence where you see them from the horizon, at the horizon at one point, and then I would say like 30 to 60 seconds later, they're covering the entire sky. Okay, so you probably know the sun is made out of plasma, right? This is superheated gas that it's so hot that electrons have been stripped from parent atoms. So what you have is like a soup of positively charged nuclei and negatively charged electrons. So the gas as a whole, it's neutral, but inside, of course, you have these charged particles flowing. So you have electric and magnetic fields inside the plasma. Okay, so that's basically what the sun is. And of course, the source of the heat, right? It's nuclear reactions taking place at the core of the star. So here you see that these particles reach Earth because there's a constant solar wind emanating from the sun, but then also these coronal mass ejections. These are explosions where the magnetic field lines, they break, and then they let loose all these charged particles at once. If the Earth is going to be in the direction of where the CME, the coronal mass ejection, is going, about 2 days later, then it will hit the Earth, okay? Because the Earth is a moving target. And then there are also coronal holes, which are, imagine, so what you see in the corner is a representation of the magnetic field of the sun. So imagine that you have some of these loops so long that they meet at, they loop at very, very large distances, could be as distant as Earth or beyond. So what you have is like a highway of high energy particles like rushing through those holes and then hitting the Earth. But it's basically a loop that it's extremely, extremely long. Okay, and as you probably have heard before, to a certain degree, the Earth, exists inside the sun. It's just that it's the part that it's not very dense. It's very, very, the density is very, very, very low, right? But we're still inside that weather, that space weather that is created by the sun. Okay, so I'm going to play a little bit of music and then I'll explain what's going on. So this is from, let's see, this is from the Solaris piece by John Estacio. So that's what you see there. It's what we call a prominence, right? So a prominence is a loop in the magnetic field of the sun that otherwise would be invisible, right? Because this is an energy field, but it gets rendered visible by the plasma. As the plasma flows along the magnetic field, then it renders the magnetic field visible. Okay, so that's why we get to see the prominence of the magnetic field because of the plasma is so hot that it's emitting its own light. In a similar way, the Earth itself has a magnetic field, and just like the sun blocks most of the UV radiation, that part of the electromagnetic spectrum, the magnetic field also deflects radiation coming from the sun in the form of high energy particles, right? So when we talk about radiation, there are two kinds of radiation, right? Radiation that it's electromagnetic energy. So those are, UV light, visible light, and so on. And then we have actual particles coming from the sun in the form of electrons and protons. And those particles are the ones that are going to be, most of them get deflected by the magnetic field. So that's good. So the magnetic field protects us from those high energy particles that, when hitting our, organisms, they could cause mutations and so on. Okay. Now, nevertheless, some particles are going to, seep through and find themselves inside the magnetic field of the Earth. They accumulate at the tail of the magnetic field, and at some point, that reservoir of particles, they become unstable. And actually, an analogy is like, imagine a rubber band just snapping. And then what happens is that when it becomes unstable and that line snap, they basically accelerate the particles towards the magnetic poles, geomagnetic poles of the Earth, and that's when the northern lights are produced. So let's take a look at an animation. This is a scientific visualization from NASA with music by Chris Ioannidis, and it's going to show more or less what I just explained. Okay, so now you know that, yes, there is a connection between the sun, right? And when the sun is very active, that's when we see, a couple of days later, we see really bright northern lights, to the point that they could be seen at lower, latitudes. But they don't come directly from the sun. They are trapped first in the magnetic field of the Earth, and then the magnetic field itself is the mechanism that accelerates them towards the atmosphere. Okay, and again, why is that important? Because without the magnetic field, those particles would not have the energies needed to see the beautiful displays that we see. So what would happen is that just the atmosphere would get buffeted by these particles, and the atmosphere would glow, but it would not have the structure that we see, in the northern lights, the beautiful displays that we see. Okay, so that, of course, they're following the magnetic field lines, and the magnetic field lines go through, the atmosphere at northern and southern latitudes. So that's why we see the lights in those regions. Okay, so the Aurora Oval is that area around the geomagnetic North Pole, and South Pole, but in this case, at North Pole, where those lines are going through the atmosphere and channeling, right, transporting those high energy particles. So if you live under that Aurora Oval, or you are just outside and you are in direct line of sight with the oval, then that's where you would see the northern lights from. So, and actually, let's go back and let's let's talk about the places where you can see them. So of course you would see them from northern Canada, would see them from southern Greenland. Look at Iceland, right? Iceland is right there in the oval. Then the Nordic countries, Norway, Sweden, Finland, Russia, Alaska, and then back to Canada. In the southern hemisphere, right, we call them Aurora Australis instead of Borealis. They are not often seen. They're produced in the same way at the same rate. It's actually kind of like a mirror image of what's happening in the north. They're not as often seen because the land masses on Earth are shifted towards the north, and there are not many cities, or land masses in the south. You have Antarctica, so there are research centers there from where you can see them, but there are no towns, there are no cities, there are no villages in Antarctica. So the southernmost points would be New Zealand. You would see them from New Zealand. When you have a chance, look at a map, look at South Africa. South Africa, of course, is the southern tip of Africa, but it's way up high. It's really not it's very far from the from extreme southern latitudes. So that means that there are not many people that can see the southern lights, because unless you're on a boat around Antarctica, you're not going to see them. So sometimes you see beautiful photographs from New Zealand, but there's not many places where you can see them. Again, equally, they produce at the same rate. It's just that don't live there. So you might recall, I'm not going to tell you what how a neon sign works, right? So a neon sign is basically what we call in the physics and chemistry lab a discharge tube. It's a glass tube that inside it has a gas or a mixture of different gases at a very low density, and then you have two electrodes at both ends. So you run electricity from one end to the other, and what is electricity? Electrons that are in motion. So as the electrons go from one end to the other, they collide with atoms or molecules in the gas, and they make them glow. So depending on the gas inside the tube, you're gonna have a different color. Okay, so here you have 5 different gases, and as you can see, they emit different colors. And actually, what you're seeing is not one single color, but it could be combination of many colors just producing one. So for those signs, what they do is they use different combinations of different gases to produce the different colors. Okay, so why am I telling you that? Because northern lights are like natural discharge tubes. Okay, you have the magnetic field lines guiding those electrons, and as the electrons go through the atmosphere, they energize atoms and molecules in the upper layers of the atmosphere. Remember that for this to happen, the gas cannot be very dense. It has to be a very, very, very low density. So of course, because of gravity, air is the densest, close to the surface. So you have to go really, really high, much higher than the airplanes. We'll see how high in a minute. It's almost a vacuum. Okay, it is almost just like the tubes. It's almost a vacuum, but of course you have particles inside, because otherwise you will not have any emission. So you see those lines, those vertical lines. Those are the magnetic field lines of the magnetic field lines of the Earth's magnetosphere render visible. Okay, so going back to what I said before, the prominence is a loop in the magnetic field of the sun that would otherwise be invisible, right? But the plasma is rendering it visible. Same thing here. The aurora, phenomenon is rendering those field lines visible. So as an astronomer, I think it's just a beautiful thing to be able to see such a beautiful display and understand, of course, the physics, being able to understand the physics behind it and say like, wow, you otherwise could not see the magnetic field of the Earth, but the aurora is rendering the magnetic field visible. So I think it's beautiful in two ways, just beautiful to see, but also beautiful that we can see that and we can understand it. So all these great accomplishments that the human mind has achieved. Okay, so here you see the magnetic field line. Okay, so what's happening with the atom or molecule? Well, first of all, you know that the spectrum, the emission spectrum of the sun is continuous, right? The sun is a black body spectrum, and it's emitting light at many wavelengths, right? And it's a continuous spectrum. And then, of course, it has what we call absorption lines because we have cooler gas in the outer layers of the atmosphere of the sun, absorbing light coming from within. But for the most part, it's a continuous spectrum, right? And that's why it's when we combine all those colors is white, and then when we pass the light through a prism, we see that actually here you see in the diagram, you see sunlight, you see all the colors. Okay, so what we see here, it's not a continuous spectrum, it's what we call a line emission spectrum, because the light is being produced at particular wavelengths or colors or energies, right? They're all related. So oxygen atoms will glow green and red. And then nitrogen molecules, notice that it's N2 and an ionized nitrogen molecule, that is a nitrogen molecule that has lost an electron. So now it has a positive charge. They emit in the red part of the spectrum, as well as on the other end, right? The blue and the violet part of the spectrum. Now, why is that? So you have a bound electron, right, in an atom or molecule. So when the electron is coming through, that free electron is going through the atmosphere, when we say that it collides with an atom, it's not a head-on collision, but it means that they feel each other's presence. And what happened is that the kinetic energy, the energy of motion of that electron, gets transferred to a bound electron. That electron, for some finite amount of time, goes to a higher energy level. And when it comes down, it gives off that energy that it absorbed in the form of a photon. Okay. And the color or energy of the photon, it's going to be exactly the energy difference between those two energy levels. The excited energy level, and then the energy level to which it goes to. It can, which is not necessarily the natural ground orbital. It can actually sometimes cascade. That is, it can go down in steps. Okay, so that's what's happening. The kinetic energy of the electron is being turned into radiative energy or photons. So oxygen will glow red and green, mostly, but I should say mostly green. It's not that it's mostly green, it's just that green is brighter, so it's easier for the human eye to see. But actually, probably in terms of, actually it's probably common as well, because even the camera, which can capture red, not always it captures the red, but the green is always there. The red will come when you have even very high energy particles coming through. Now, for things dealing with, remember I told you that for this to happen, the atmosphere has to be almost a vacuum. So because of that connection to the density, the red can occur only when or where the air is even less dense. So that's why we see green, and above where air is less dense, we see the red. Okay, and that has to do something with, you know, radiative lifetimes and, you know, things dealing with, you know, with a physical process. And I go, you know, in other talks where, you know, we have more time to talk about the science, we go into more detail. But the important thing to know is that the fact that the reason why the red is above the green is because for that red to occur, that red emission, the air has to be less dense. Okay, and then closer. Okay, so let me go back and show you the heights. Look at these heights. It's 150 to 250 kilometers. Okay, so we're talking about, this is kind of like ISS, you know, distance. So it's very, 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 very high. So the auroras don't occur where the regular, you know, weather occurs. Okay, so not where, you know, not where clouds are forming and storms, and not even where airplanes are flying. This is much, much higher. Okay, now from 100 kilometers to 150, so lower, that's where green is going to dominate. Again, from the oxygen atoms. Now look at this photograph. The sky is so green that even the ground looks green because it's reflecting all this light from the sky. And then in the winter, we can see something similar, but of course with snow reflecting all of that light. So here, you know, you don't see the lights in the sky. It's because the lights are kind of like above me and a little bit behind. So it's reflecting all that light back to the camera. Okay, so it reaches a point where the air is too dense for the lights to form, and that's why you get that lower edge. So you see the red, very high altitudes, you see the green, and then, you know, the air is too thick. And actually it's too thick for two reasons. You know, one is what I was telling you about, the, you know, the physical or atomic processes that are taking place, but also because you need oxygen atoms. And closer to us, closer to the ground, what is it that we have? We have more oxygen molecules, not atoms. And in case you didn't know, I'll tell you, one of the sources of oxygen atoms, it's basically oxygen molecules being broken apart by UV radiation. Okay, so UV, it's so energetic that when it comes through the atmosphere, it can disassociate, if I'm not mistaken, it's actually O3, which is ozone. It can break ozone into O2 and O in an oxygen atom, okay? And the oxygen atom is the one producing the northern lights, not the oxygen molecule, okay? So at certain point, all that UV has been absorbed, so UV cannot, you know, and thank God, right, that we don't get a lot of UV on the surface because most of it is absorbed. We still do get it, otherwise we would not get sunburn. But most of the UV light gets absorbed. So at some point there are not enough oxygen atoms to glow. So that's why you get that lower edge. Okay. So here you get, you know, and again, so this is the neat thing about photographing the northern lights over and over and over, you know. Started going in 2014 in March, and ever since, except for, you know, this pandemic, ever since I've been going twice a year, March and September, March and September. Again, first because I was producing more and more films, and then because I started, you know, leading tours. So that all those photographs have given me a huge catalog where I can, when talking about the morphology and, you know, all these aspects of the northern lights, I can just pull my photographs and say, hey, let me actually, this is a good photograph to represent a or B or C. So here you see very clearly that lower edge, then the red aurora, and the altitudes, right? So look, 100 kilometers, about 62 miles. So they start around 62 miles up. Mean free MFP, that means mean free path, and that is the average distance that an electron can travel through the atmosphere before being absorbed. So of course, if the atmosphere is very thin, it can travel a long distance. So 200 kilometers up, the free electron can travel 4-5 kilometers before encountering another particle. But when you're down to 100 kilometers, it's only 1 meter. Okay, and like I said, then as the Earth gets thicker, then that distance is less and less, and you cannot, for another reason, you cannot produce more northern lights. Okay, there is another red, they call it like a lower red. I call it more like, it's more like a magenta, and it occurs just below the green. Okay, so that one is not coming from oxygen atoms. That one is coming from nitrogen molecules. Let me show you a couple of examples. So this is looking straight up, and you see that magenta just below the green. You see that during not during a normal display, but during an event called a substorm. And that's when people say that, oh, so the northern lights, and they look like they were dancing, they were doing their dance. That's a substorm. That's when you see them moving very, very rapidly, and that's when you see that bright magenta under the green. There's yet another beautiful color. It's like a blue purple. That one happens during twilight, because it's the combination of, you get that emission, but it's also the aurora. Those gases are also interacting with sunlight. So of course here the sun has set for us on the ground, but but at that position up in the sky, sunlight is still hitting that part of the atmosphere. So you get another atomic effect, and you get that beautiful blue purple light. But again, so and then of course at some point, not even at that elevation, can see the sun. So the sun completely sets. So that's why you see it only during the twilight. Okay, so let me give you, so in some of these photographs, you'll see like a yellow aurora. So yellow, there's no yellow emission. That is, there's no atom or molecule emitting yellow light. It's just that along the same line of sight, you're seeing red aurora and green aurora. And when you combine those two colors, you get yellow. Same thing if you're seeing blue aurora, and in that same direction you see red aurora, you can get like a pink. Okay, so this photograph shows you a little bit of all of that. Let's see, you get the red from atomic oxygen, the green from atomic oxygen, yellow, combination of red and green, and then you get some blue, right? You get it to the left of the of that curtain, blue and purple, that comes from nitrogen. And then when you combine red and blue, you get that pink aurora, which is kind of like in the middle. So again, yeah, and that's why, you will not always, you will see these things that I'm showing you. So that's what's great about just photographing like crazy and having cameras taking time-lapse sequences, because then you get to photograph all of these things. Now, for you astronomy buffs, you know your astronomical objects very well. So here, look at the Hyades cluster. Look how close to the horizon it is. This is latitude, by the way, this is latitude 62.5. So Andromeda Galaxy is most of the time you know, in the sky. I don't even, you know, maybe it's even circumpolar. I don't remember the declination, but in most of my photographs, the Andromeda Galaxy is, you know, somewhere in the sky. The other thing that was very surprising for me. So I have photographed the Milky Way from Chile, right? From Chile, from South Africa. I've seen it from Australia. So I'm used to seeing the galactic center up in the sky. And as you know, the outskirts of the galaxy, it's not as impressive, right? Because you're going through less material in the Milky Way. But Yellowknife is so dark that look at the outer edges of the Milky Way. I mean, it still looks impressive, and that's just because, you know, you're away from, you know, city lights and it's so dark. Okay, I'm gonna go through equipment kind of quickly because I don't want this to become like too technical. And let me just tell you, of course, if you have any questions, you can, you know, always email me. But these are things that I go through when people join me in Yellowknife, because the idea is that, hey, if you can just come and enjoy enjoying the Northern Lights is the you know, priority. I was maybe second on the list is actually understanding what's going on, and that's why I give a science lecture, you know, in Yellowknife. And the third one is, hey, if you want to photograph them, then I can tell you, you know, which equipment to get. But nowadays, even with a smartphone, you can take beautiful images of the Northern Lights, because now smartphones, you know, can take long exposures, you know, and like on the iPhone, that night mode, it's basically a long exposure, and you see that it tells you, okay, I need 3 seconds, keep the camera still. So while the camera takes a long exposure, that's basically what it's doing. But of course, if you put it on a tripod, then you'll get better results. So, you know, lenses, you need fast lenses meaning, again, just like telescopes, right? That a big collecting area. So big lenses, small f number like 2.8, and really wide lenses, because you know, and again, for those of you who do a little bit of astrophotography, you know that usually you want magnification, right? Because you're photographing these objects in the sky that are fairly small for the most part, unless you're photographing like the Milky Way. Of course, you want a wide angle for that. So for the Northern Lights, you saw in some of those photographs, they can take a big chunk of the sky. So you need a really wide angle. So these are just different, you know, lenses that I use that are wide and fast. Here is a good example. The diagonal field of view of this photograph is 114 degrees. And look, notice that I'm not photographing the whole structure in one frame. Okay, and then I overlaid again, because I know that you're stargazers, so you know, have an idea of how big the sky looks like by look at all these constellations in one single photograph. Here I'm stacking photographs from a time-lapse sequence to show, right, the star trails, to show the rotation of Earth. And look at that yellow. Again, not an emission, but a combination of colors. That's another fast lens. You can do, you know, fisheye photography. Okay, so this is really wide. Here, the diagonal field of view is 180 degrees. Okay, the reason why the photograph doesn't look curved is because, or I should say the horizon doesn't look curved, is because I'm pointing at the horizon. So the horizon is right there in the middle of the photograph. That way I avoid the curved horizon, which I'm not a fan of. If it's a fisheye, circular fisheye, that's okay. But if it's one of those lenses that you get the distortion, you know, I don't like the horizon distorted. But of course, if you get a circular fisheye lens, then, you know, you can point it up and you can photograph the entire sky. Okay, this is, you know, the Arecibo Observatory, rest in peace. Okay, and then of course you have to put your camera on a stable tripod. If you get a carbon fiber tripod, then those are really light, really expensive, but very, very light. Batteries, internal batteries are getting better and better, but now also you can connect, if you can connect it to an external power supply, even better. So you could bring like a big USB battery, and now new cameras have like USB-C, and then you can plug it directly and feed the camera. Okay, and then of course, you can get like a level, make sure that you're pointing it straight. As you can imagine, it's so dark, that it's hard to see like even the horizon. So it's better to have all these aids, so you know that you're pointing straight up. And then if you want to give another dimension to if you're doing time-lapse photography, right? That's when you program your camera to take one photograph to another one, and then you compile them and you can make a movie. If you want to give it yet another dimension, you can get a motion control system. That's basically, a device that moves the camera between exposures. So then you get, it's like a dolly. So you get a different perspective as you get the sequence. Intervalometers. Back in, when I started doing like, time lapse, astro time lapse, cameras didn't have internal intervalometers, so you would have to get an external device. Now cameras, you can do it with your camera, and actually you can even do it with your smartphone. Your camera app, at least on the iPhone, you can program it and take a time lapse, and it will make a movie for you. I'm going to give you my general website at the end, but there I have a link to my Flickr account, and on my Flickr account you can see a bunch of these photographs. Okay, so there's so much to share, so I'm gonna speed up, try to hit the 5 minute after the hour, so it can be 1 hour exactly. So things that you can enjoy. Sometimes the structures are homogeneous, that is that you don't see the the lines, but sometimes you see the lines very, very, very clearly. The corona, that's when the northern lights are right above you, and you get two curtains, and then you just like train tracks, they appear to meet at infinity, so you get that beautiful point of view. And you get folds, so they're constantly changing shape. So you get folds and multiple folds, and even smaller folds like kinks that travel through the display, through that curtain very, very, very quickly. That's why it's so neat to take time-lapse sequences, because then you can play the movie and then you can see how they change. After one of those substorms, when I told you that the northern lights, they dance, then it gets like diffuse. And it's almost like an overcast sky, but it's not overcast. It's actually the auroras that it loses its structure, so the whole atmosphere glows. You can see them pulsating. Sometimes, not always. And this happens. I think this happens after substorms. You see them pulsating. So this is taken with a night camera called the Aurora. It's called the Aurora, but it's not necessarily made for photograph auroras. It's for people who have boats and people and hunters, people who need to see at night. So this is real time. Okay, look how fast the aurora is moving. Okay, so this is during a substorm. When not in a substorm, you see the aurora changing shape very, very slowly. So this will last for many minutes. I've seen events that last more than 10 minutes, 10 minutes of this. I think I have a video that I think it was close to 20 minutes. Okay. So this is when they say that the aurora is dancing. So this is this is a substorm. Okay. Okay, so this is the sequence that I was telling you, that I think in real time, it took less than a minute to go from the horizon to covering the entire sky. Okay, so this happens in Yellowknife because you're right under the Aurora Oval. Okay, and then this shows you from that quiet display that I was telling you about into a substorm. So look how active it becomes. And then it turns, diffuse, and then it turns back into, discrete structure. So it alternates. Because the way the human brain has evolved, we don't see colors very well at night when the light levels are low. And that's why, like, think about it, if you're on the highway driving, it's hard to see the colors of cars. And it's not because it's dark, it's because they're what's working in the retina is the cones, not the rods, the cones, and I'm sorry, the rods. So the rods, they basically concentrate on capturing different levels of brightness, but not colors. The colors, we start to detect colors after the intensity of light goes beyond a certain threshold. So the human eye kind of like sees like a muted green, but then of course the camera sees more color. Okay, so it's a limitation of the human eye. But the magenta, that's why the magenta, you can see the magenta clearly, even easier than the red, that red above the green. That's because during the substorm, the aurora becomes really, really bright, and then the human eye starts picking up color. Okay, so Yellowknife, why is it great? First of all, it's very, very dry. So if it's very dry, you're not going to have a lot of precipitation. So that means that you're not going to get a lot of rain and a lot of snow. Okay, so what you need is clear skies. If the skies are overcast, you're not going to see the lights because the lights occur at a much higher elevations. Granted, if there are breaks between the clouds, you can see them, and that can be interesting. But you want to see the full show. So you have to avoid the summer months because this is so high up north that during the summer months you have the nighttime is either very short, or what you get is just a long twilight, but it doesn't get dark enough. So you have to go starting at the end of August and then all the way to like March or April, but then you have to avoid certain months that are usually cloudy. That's why I go and I lead tours on the clear months, or the months that the chances of getting clear skies are higher, and those are March and then September. Those are the best months. Okay, or Yellowknife is fairly flat. They have hills. Actually, this is funny. I gave this talk in Puerto Rico, and in Puerto Rico, of course, we have hills and mountains. And I said that there are hills in Yellowknife, and this friend of mine who went with me, he said that I was basically BSing, because it's like, wow, come on, you're selling these people that there are hills. There are no hills. And I'm like, wow, you haven't been to Chicago. I mean, you haven't been to the Midwest. Midwest is really, really flat, right? With the exception of some, when you get close to rivers and so on, and you get interesting features. That to me, that Chicago is flat. This here, no, you get interesting, you get much more hills. They're not very, very tall, but for photography, they're interesting. But at the same time, you don't get the tall mountains that you might get in other places, where they might be so high that they might even cover, or obstruct the northern lights. So it's neat that it's beautiful, it's interesting, but you can still see the northern lights without getting obstructions. Okay, so here, for example, you see, it's always this terrain where it's not flat. It's you get these outcrops and hills, and even gorges. So this is in September, of course. In March, the lakes get frozen, which is interesting because so then we can drive on them. Okay, so here, look, for example, look at this. I mean, this is probably just, I don't know, maybe 100 feet in height, this structure here where I'm standing. So, you know, to me, that's not it's not flat. It's just that you don't have, you know, you don't have tall mountains. Okay, so this is drone footage of this particular place. So for those of you who are, well, actually, for two reasons. The landscape is beautiful. So during the day, we take hikes and we go out and see nature. And then if you're into photography, even better, right? Because you can photograph this during the day. And then when you're photographing the northern lights, you can photograph the northern lights in the context of, you know, of the landscape. Okay, we learn about First Nation, you know, cultures. There's a First Nation group called the Dene people. So we go into teepees and we go into villages and so on. So there are cultural aspects, very picturesque. In September, we go on, you know, bike tours around Yellowknife. Then you get the reflection of the water, which is beautiful. This is from Yellowknife itself. Okay, population is 19,000. So if you go into the old part of town, even with the city lights behind you, look, you can still see the lights. But for the most part, we go out into the boonies to see the lights. Okay, this is also video. So this is real time. Let me speed it up a little bit so we can save some time. But here, so you can see how. It's again beautiful. You know, they evolved during the substorm, and then in the winter, the landscape is beautiful. It looks absolutely, you know, completely different, but it's also absolutely beautiful. Everything's white. Lakes are frozen. They make ice roads, so we can drive on them. We go duck sledding. Okay, they have an ice castle, ice and snow castle. Like I said, we actually drive. That's a nice road. So look at that. No, and again, you see, so the landscape is pretty. You know, you get the hills, you get the trees, and so on. You can get closer to the trees. You can photograph, you know, between the trees. But you don't get high obstructions. If you were in Anchorage, and I mean, again, Anchorage is beautiful, but you could have a big mountain covering, you know, a significant fraction of that display. Not to mention that you're not as north as Fairbanks or Yellowknife. Okay, so I'm just gonna go. So if you go to this website, josefranciscosalgado.com, it's kind of like a portal, and from there you can learn about, you know, KV265 and the films. You can see, you can click and get information about the tours. Go to the tours website, Flickr account, Facebook. You know, feel free to send me an invite if we're not connected, and that's basically it. So now we can answer some questions. I'm gonna stop sharing so we can see each other. Okay, there we go. Yes. If you're muted.
Jose, can you hear me?
I can.
Okay, I was in Finland.
In Finland.
Yeah, I was in Finland in March, and we didn't have that much in the way of nighttime. It got light really quick, about 3:45 in the morning. So
Wow.
March was not a time, at least in Finland.
So you know what? Yeah, I would have to see the latitude. Probably it's even north of 62.5. So Yellowknife is 62.5. So maybe
it was north.
Yeah, north. Right. And do you know were you south or north of the Arctic Circle? you know,
I
if it
think
was
I was
actually,
north.
oh, then definitely higher. So that's why, exactly. So the higher you go, then the more you have to avoid the equinoxes, right? So March
Yeah,
21st,
yeah.
September 21st, exactly. So you have to go like in the middle of winter. And by the way, in Yellowknife, you can go in January and February. It's just that the temperature is like -40. You know,
Yeah, yeah.
exactly, -40.
Well, as
So
long as you dress for it, it's okay.
yeah, it's but nevertheless, you know, actually what I experienced at the South Pole was I think it was -40, -60 with the wind. So yeah, I mean, but then you have to, the thing about, you know, the Northern Lights is you want to be outside as much as possible. So there are places, right, where they have a cabin, but then you have to go back, you know, back and forth, right, in and out to warm yourself or go inside a vehicle. So the neat thing is, you know, to be outside as much as possible.
Yeah, and then your batteries will.
Your battery, yeah, absolutely. The batteries are a big challenge, and your phone as well. If you want to use an app or you want to use it, you know, forget about it. It's just gonna die. So in March, we didn't talk about temperatures. In September, it drops at most to like freezing point. So for people from Chicago, that's piece of cake, right? Good down jacket, and it's in the 30s. And I'm talking about like 2 a.m., you know, so in the middle of the night. In March, it can drop at night to like maybe -10. But like you said, with the good gear, and what we do is that I have my own gear because of course I go twice a year, but for participants, they can rent it in Yellowknife. And it's very inexpensive to rent the whole thing, the parka and the boots and the snow pants, everything. And then like you said, I mean, you're comfortable if you are well dressed. It's not an issue.
Yeah, but even in 30-degree weather, you still have to worry about your batteries.
Yes. Yeah, definitely.
Jose,
Okay.
what are some typical exposure times? For
Yeah,
your
yeah, great question. So I usually set my camera like my you know, middle of the ground standard ISO setting is 5,000. Okay,
Wow.
these camera 5,000, yeah. And actually in my cameras, you know, I can push it 64 and so on, but I try not to, right? Because I want to get the best quality as possible. So 5,000 the camera does well. So I usually leave it at 5,000, and then the lens, most of them are 2.8. I have some that are faster, right? 1.8, 1.4. And then the times, what I do is you know, of course, I look at my histogram and see if it's too bright or too dark. But they typically, a typical exposure, I would say that it's around 4 seconds. If I go, it's not bad. If I go beyond 4 seconds, 6, 8, 10, it's because I can see that, yeah, it's there, but it's not really bright. It's very rare that I take like 10 or 12 seconds. Very rare. Usually like middle of the ground, it's 4 seconds. Now, the neat thing is the following. If you're taking time lapse, it works very well to our advantage, because when the substorm, you know, it's taking place, it's changing very quickly, right? But it's also getting very bright. So you can decrease your exposure time. You can bring it down to 3, 2, even 1 second. And then if you're doing time lapse, then that's a better sampling rate, right? Because it's occurring, it's moving so fast that if you were to take a long exposure, you will blur and lose the resolution of what's happening, right? Which actually, you know, photographically, it can look beautiful. But if you're taking a time lapse sequence and things are changing very fast, you want to keep those long exposures really short, right? But it works well. Why? Because they're not only faster, but they're also brighter. So it works to our advantage. Yeah.
Thank you.
Now, do you actually see the green, or is it just seen by the camera? Because
No,
when I was in Finland, I just saw white and people picked up green with their cameras.
no, you can see the green. Like I said, it all depends on how bright the aurora is. The
Yeah, it
brighter the
wasn't
aurora,
bright.
right. So the brighter the aurora, then that's where the brain starts picking up colors, because it's just,
Okay.
it's just brighter. That's why, like I said, that's during the substorm, the aurora, that's when the aurora is the brightest, and that magenta below the green, with no doubt, you can pick up that color, but it's because
Visually.
it
Okay,
visually, yeah.
The other question I have, you were talking about time lapse with stills, but with video, you don't do time lapse. So how are you going to pick up color with video?
Okay,
If it's
so with video, now it's when we're actually pushing the current technology, right? So what we need is a camera that can perform well at high ISO. So I push the ISO, I don't know, 24,000, like really, really, really high. But also I have to get the fastest lens that I can get. That's why I bought that Sigma lens, that it's 20 millimeters. It's, I rather have it wider, but hey, 20 millimeters, it's still wide, but it's 1.4. So, right, so it's capturing even more light. And then of course, video, you can take 24 frames per second. So that means that it's 1/24th of a second. So you're trying, right, to capture as much light as possible. So it's a combination of a camera that performs well in the night with 24 frames per second instead of 30, and then the fastest lens possible. What I wish is that a camera would let me take, straight video, but then that it would let me choose a slower frame rate, 15, even 12. Think about it, 12 frames per second, which I think it's still for a video, it's still fast enough. And it's double, it would be double the amount of light that it would
exposure, yeah.
capture, right? Compared to 24 frames per second. But yeah, the slowest is 24. But cameras, I mean, they're getting better and better and better. So that's why I'm just exploring, I just started to explore with video. But that's the other funny thing. I've been to Yellowknife so many times. I have so many time-lapse sequences that in my last trips, what really started exciting me, it's like, okay, now capture real-time video, because I can show people how fast they can actually move and so on. And then of course, September of 2019 was really good. Actually, I have to tell you, it was really good, but not as good, I would say, as 2014, because 2014 was closer to solar max than solar minimum. But what's been happening during the pandemic, let me put it this way: if the pandemic was gonna hit, thank God it didn't hit during solar max. So the pandemic hit in solar minimum, but now, as I have a lot of friends in Yellowknife, and I see what they post on Facebook. Oh man, the activities, it's going up. It's beautiful, beautiful. So by the way, I have dates blocked. If you go to the website, I have dates blocked at the hotel for March and for September. What I'm waiting for, it's not on the US side, right? We can travel probably on the way back. We have to show a negative test and so on. But it's NWT, the Northwest Territories, right? Yellowknife is the capital city of NWT. It's like a province, but it's actually technically a territory. So you have two restrictions: the federal Canadian government, but then also NWT has its own restrictions. And it's understandable. They're up north, they're covering a big area, and they have one major hospital in Yellowknife.
Oh yeah.
So of course, you can see that they're protecting themselves, and they cannot, overwhelm, the hospital. So people, you have indigenous people traveling from all over NWT going to Yellowknife for medical services. So of course, you cannot overwhelm the system. What I've heard is that now if they start vaccinating children, then that will put them over the threshold that they're trying to reach. So most people will be vaccinated, and hopefully, fingers crossed, I'll be able to go in March. So I haven't been able to go since September 2019. So, but
And
I'm
of
ready.
course,
Mhm.
and of course, once you buy your new cameras and that you can push to this level, they'll come up with something else and it'll be obsolete.
Right. So that what's coming, you know that now cameras are like, mirrorless, right? That's the new thing.
Yes,
And
yes.
for example, Nikon has the Z5, Z6, Z7. So what's happening, I think it's at the end of this month, it's their first pro camera, like the D5 and the D6, but mirrorless, but again, I mean, those we're talking about, I use them because I use them professionally, but even I use them professionally, it hurts because it's like 6K. They're really, well, they're really expensive. Again, it's not that you need that kind of camera. It's just that it has other advantages. One
Yeah,
of
you
its
buy
big,
6,000 and then it's obsolete.
well, I'm still using my, D4 and D5. It's just that they get better and better, but they still continue performing well. One of the main advantages of those pro cameras is that the battery takes it's like half the width of the body. So I can photograph with one of those big batteries all night long.
Oh,
And that's the other thing with mirrorless, because of course it's electronic, they consume more power. So for nighttime photography, you better have, like you said, a bunch of those batteries that you can be swapping, or something that I haven't tried yet is then have a big power supply that then you can have a USB-C and just run it off the power supply. But in March, then you have the other challenge, right? Which is the cold weather will shorten the lifetime of the battery at night. So anyway, it's fun and challenging.
So because of those temperature limitations for the battery, do you have any procedures for protecting your gear from the cold so it continues to function?
No. Let me tell you, there is something. I did buy something that I haven't used yet, which is kind of like a cover. It's like an all-weather cover. So it not only it protects from the rain, but it also insulates a little bit. What people do is, and actually for those of you who have telescopes, you know that you can get like these rings to protect from the dew, right? So dew doesn't form.
Dew zapper,
Right? So it's something like that you can put, what you want to do. You want to keep the, especially lenses like these, depending on the dew point, right? You're exposing the glass and they can fog. So they do that. And then the other thing that people do is they take, of course, we have hand warmers all the time. You put inside your gloves. So you can take a couple of those and you can wrap them around the body, and maybe with Velcro or a rubber band, you can keep the camera warm. The thing is this: in Yellowknife, a camera has failed to me for only once. I have a Nikon camera that in the middle of the sequence, I was getting half of the frame was completely dark. But again, it's not a permanent problem. I put it inside the car and then it gets warm and then it continues to work properly. But it's 10 minus 10, it's not cold enough that the shutter is going to freeze or anything like that. No. Of course, Nikon and Canon and Sony are not going to tell you that you can operate it. Probably say like, oh, 10 degrees over, but no, they have never frozen. So nothing permanent, only a temporary problem with one camera, and one in many, many nights. I have spent like 60 nights in Yellowknife. Only one I encountered a problem. On the other hand, a shutter did freeze on the South Pole. And I was taking photographs, and all of a sudden it made the most awful noise, like like this, like
In the middle of the dark too.
no, during the day, because I went to the South Pole in the spring, but it was -40, and it was like, and I'm like, oh my Lord, I broke the camera. So I went inside the South Pole telescope. It got warm. Okay, let me try, and it just worked. It just worked, but I did, of course, that I didn't want to push. But in Yellowknife, no, I guess -10. Yeah, you might see something funky with the image, but it not a permanent. Yeah, not a. So you know what Yeah, sorry, Claire. Let me just say this.
The other question I have is about the wind. You can have -40, and if there's no wind, it probably is bearable. But if you even have a slight breeze at
Right.
-40, you're going to.
Right. So the good thing about Yellowknife, it's not windy. It's not windy. So usually that lake is going to be, very, very, very quiet. You get a nice reflection, and it's not breezy. So anyway, there are all these gadgets to protect the cameras. But you know what? You know how many tripods, cameras, and lenses I bring? I can't and won't bring even more gadgets. Just this to keep it warm and this to cover. It's like, you know what? It's too much. So if it stops working, that's fine. I usually have 3 cameras. Anyway, very rare. What's more annoying though, it's the fog. That, and then you can use, you can wrap, and that has happened a few times. But that's kind of sad that you're taking a sequence, and then in the middle of the sequence it fogged up, and so. But again, it happens sometimes, and it's usually in September. In March it's drier. So anyway, Yellowknife is dry, so that's not a common problem. So that's good.
Okay. Thank you.
Yeah, you're welcome.
Jose, I especially liked some of your auroras set to music. Is any of that available online? I seem to recall one sequence set to the 1812 overture, and I just loved it. And I'm just wondering if.
But not mine.
Oh, okay.
No, not mine. I haven't done 1812. Yeah, on the website there are clips. Actually, the planets is the big one. If you go to KV265, you can see a little bit of Mars. Yeah, I haven't done 1812. Actually, that would be neat. But no, and actually, I should tell you, I made a film about the night sky. And from different locations on Earth, and of course the Milky Way and moonlight and starlight and northern lights. Hopefully it will be premiered with Chicago Sinfonietta at Symphony Center whenever whenever the pandemic is over and they can have a big event. They're not going to have something for a fraction.
They are now, the Chicago Symphony is now having a half subscription, half a year of regular concerts.
Okay.
And I think next year they'll probably go full bore, but you have to show your proof of vaccination before they let you in.
So this would be with Chicago Sinfonietta, but it's the same place. It's a symphony center, and hopefully it will be during the concert season 22-23. So we'll see. Anyway, it's something that you'll enjoy. And you know what? Actually, I will, Jim. I will let you know, because usually what we do when we have concerts is we invite you guys, and then in the suburbs we invite Naperville folks, so you can bring telescopes and interact with people and so on. So if it happens, I'll make sure. And the same thing with Cernan, we'll let them know. I think last time we had a concert there, which was 2014. I think Cernan was there, Kavli was there, definitely CAS. So anyway, yeah, I'll let you know if it happens.
Appreciate
Okay,
it.
and how do we sign up for your trips?
So just go, if you go to the website, you'll see the information there. You just go to josefranciscosalgado.com, and it will take you to the Aurora website, and the dates are there, and information, and my
Okay.
phone number is there, my email address is there. So like I said, and let me quickly take a look. I'm there. The tour website is JF Salgado. So right now I have week number 1, February 27 to March 5th, and then a second week, March 6th to March 12th, and then 2 weeks in September. So like I said, I'm set with a hotel. What I'm waiting for is the NWT government to basically open the doors for non-Canadian tourists.
Right.
What about then running trips to Fairbanks? Because then you don't have that foreign country.
Yeah, that's
complication.
yeah, that's a possibility. I mean, I could always do that. It's just that I'm set in Yellowknife. I'm licensed
Yeah.
there. I have my contacts and so on. But yeah, if the Canadians don't open up, then that's definitely a good alternative.
Yeah. Okay. Thank you very much.
Oh, thank you. Thank you, Claire.
Earlier, you
What-
said that oxygen
Ah.
emissions were more dominant in the higher atmosphere. Do you know if that means that your friend on the ISS had a better view of the red emissions?
That's a really good question. Maybe, but again, the thing is that with the perspective is going to be definitely different, but in terms of the human eye, it's the same thing. In terms of like the aurora itself has to be really bright, and it's not necessarily it's not going to be brighter, so your point of view is changing. Definitely the perspective is different in the sense that you would see red and then green below instead of like the other way around. But in terms of the brightness, I think it would be basically the same thing. It would be basically the same thing.
You're saying it would look kind of white, like on the ground as well?
Yeah, when it looks kind of white, it looks very pale. It's because it's not very bright. But as soon as it becomes brighter, those colors, you start picking up those colors. But those colors are there. It's just a matter of the magnitude of the brightness.
Are there any other questions? If not, Jose, I can't thank you enough. Yellowknife is on my bucket list,
Me too.
along with a number of people in the society. So, we'll be in touch, and I can't thank you enough for the time and effort to brighten up our day.
You're very welcome. Thank you so much for the invitation, and yeah.
Thank you, Jim.
Yeah.
Thank you, Jim, for setting this up.
Well, actually, the credit for that goes to Wayne.
Oh, thank you, Wayne.
All I do is give him the speaker, and then he sets it up by Zoom. I have no idea how he does it, and I'm not particularly interested in learning. So, thanks, to Wayne and Chris and the folks at Cernan. And I don't have a confirmed speaker for next month, but I'm working on one, and hopefully, we'll have another Zoom meeting in November.
Okay.
Wonderful.
Very
Sounds
well.
great.
Well, thank you. Thanks for the invitation.
Thank you. Bye-bye.
Okay, bye.